Start or no?
No.
Okay, so yesterday we did a bunch of Pivner type equation, problems. Hopefully you're comfortable with them. And I wanted to do one today. Well, I'm going to do two today, but I wanted to start with this one, which is a stoichiometry problem, but it's just dealing with gas. So I'm going to read it and then we'll try to do it. So sodium azide, which is the common name of that compound, NaN3. Sodium azide is used in some automobile airbags. The impact of a collision triggers the decomposition of sodium azide, and then they show you the reaction that it undergoes, and then a bunch more fluff. This is all fluff information, blah, blah, blah. You go to the bottom, it actually asks you the problem. Calculate the volume of N2 generated at that temperature and that pressure by the decomposition of 60 grams of sodium azide. So this is, it's a stoichiometry problem. So think to chapter 4, and it's basically, I'm giving you a starting material and I'm giving you an amount of a starting material, and I want you to tell me something about one of the products. So if you knew how to do it in chapter 4, then this is exactly the same process, just a little different. So can anybody tell me how I would start this problem? So just to write it, they want volume of this guy, and they give you 60 grams of this guy. And they give you other information, but 60 grams, just write that, 60 grams. So how would I start this? What's the first thing I should do? And it's balanced, so you don't have to say that.
Do we start with Pivnert?
So what would you do with Pivnert?
So with Pivnert, we would cross out the things that aren't mentioned, correct?
So okay, yes. So let me, I'm just going to play along, right? So this is not different conditions. Remember, because that's what we did yesterday or whatever. Yeah, yesterday. I don't remember. Anyway, that's what we did the last time. And you tend to cross things out when they don't mention them. That's true. But usually that happens when you have those two different conditions. This is just a straight up question about a reaction, right? So, but no, but I'm not saying you're wrong. So what they gave you temperature, they gave you pressure, and yes, R would be different, right? I mean, R would be constant, but I guess where would you go from Pivnert? What would you do with that?
You would get the volume on one side.
So what are you trying to solve for? You're going to get volume? You're going to try to solve for volume?
Yes, the volume of N2, correct?
But you don't know that. How, okay, fine. Volume of N2. So let's do nRT over P, right? And then you would solve and you would get a volume. That would give you a volume. But how are you going to get this?
Convert the number of moles of NaN3 and convert until you get moles of N2.
Okay, so that is the first step, Cherish. Because that's right. So when I asked what's the first thing you should do, is that's the first thing you should do, since you're right, because you're going to eventually use this exactly the way that you stated it. But the first thing you should do is convert, because you have information about a reactant, but they're not asking you about a reactant. Oh, and it's this guy, sorry, volume of this guy. They're not asking you about a reactant, they're asking you about a product. So you can first, convert the grams to moles of NaN3. And then when you do that, then what can you do? Then what do you do? Like you said.
After that, you also convert the 8 degrees Celsius to Kelvin.
No, sweetheart, but what I'm saying, staying with this, right? So you said 60.0 grams of NaN3, right? And you said convert it to moles, right?
Yes.
Okay, but then what do you do from here? Do you plug, once you get this moles, do you plug this answer into here?
No, you keep going, so you have to keep going until you get moles of N2.
Okay, that's what I'm asking. So the first step is usually that. But if that's what you were going to do just backwards, that's fine. But for continuity purposes, that's the first thing you would do, is you would convert the NaN3, convert it to moles. That's usually a first good step, but you're in moles of the wrong person. So then you would have to use, what is that called? Mole to mole ratio to get to the right person. So then you would put what down here?
You put moles of NaN3 down there.
So tell me the number.
The number is going to be 2.
Okay, and then what goes on top?
On top is going to be 3 moles of N2.
Perfect. Now you have, can somebody tell me what NaN3 is? What the mass is?
65.02.
Okay, 55.02. So then can someone give me this answer?
65.
Oh, 65, my bad. So now can someone give me this answer?
$1.38
Okay, 1.38 squids
moles
of,
N2.
yes ma'am. Okay, 1.38 moles of N2. Now we can plug it in, Cherish. So because now we're in the person that they want. So now we use, yes, now we would convert the 80 degrees Celsius to Kelvin. We would convert this to ATM, and then we would use exactly what you said. Just plug everything in that we have and use and get the volume. So do you guys want me to plug it in, or do you understand what you need to do from here?
Can you plug it in?
Fine. So V is equal to nRT over P. So it would be 1.38 moles. And I'm sorry, I'm writing vertically. So R is 0.082057 liter ATM mole K. Times temperature. What is 273 plus 80? 373, 353? 0.15 Kelvin over, I don't know this. What's 823 divided by 760?
1.08.
1.08 ATM. There you go, Miss Glover. So everything cancels, mole, mole, K, K. You're left with liters, which is what they want. Answer. There you go. So any questions? You're welcome, darling. Any questions? So no questions. Okay. So that is a typical, just so you guys can understand that the stoichiometry stuff that we did in chapter 4 can still apply, right, to what we're doing in chapter 5. It's just now we have gases, or we can apply the Pivner equation to help us either before or after the, in the problem. So I'm going to do one similarly, well, not similarly, but almost similarly. Well, it's a gas stoichiometry problem, but it's going to employ one of the gas laws, which is very important that you understand how to do that so that you don't waste time plugging and chugging all the time, because you can have a quicker way to do it if you just apply one of the gas laws, or all of the gas laws, but we're doing one specifically. Okay, so I want to do, as we talked about in the class yesterday, at the end of the class, we talked about using Pivnert as, I'm going to put you guys down, using Pivner as a way to get density, right? And I sort of quickly showed you why that works. So I want to go over that again, but I would like you guys to help me. So remember what I said about this guy. This symbol right here is moles, and that's what it is, but it's moles because it actually is something else that converts to moles. So do you guys remember what that is?
Is it moles over molar mass?
No, it's not moles over. If you did that, look what you're telling me to do. Moles over molar mass. How if I flip this equation, this is going to be moles over grams. How is that going to end up being moles? So it's not moles over molar mass. It's what over molar mass? Oh, you were breaking up. Say that again, sorry.
Grams over molar mass.
Yes, so I think I heard you. You said grams over molar mass. That is correct. When you flip this over, it becomes moles over grams. You don't have this anymore. So now this cancels and you're left with moles, which is why the symbol N is equal to moles. Okay, so the fact that you can do that is now gives us an opportunity to again find density. I'm going to show you, and then it also helps you find molar mass of gases. So if I was to substitute what N really is, and these are just the symbols, okay? So N is equal to little m over squirrely m. This guy is grams, this guy is molar mass, okay? Those are the symbols. So if I just insert that instead of the N, instead of the Nancy, I put the little m over the squirrely m, I would have this, right? I just, substituted it. Now, I want to find density of a gas. What are the units of density?
Mass over volume.
Thank you. So mass over volume, here you have mass, here you have volume. So all you got to do is isolate those two variables on the same side. So you would do mass, and I'm doing this in one step, so you got to stay with me. I got to bring the molar mass up here. So I'm going to and I have to bring the volume to the other side. So I'm literally just switching those, right? That's all I've done. And then these two guys have to be divided to the other side. So I would have this. So if you see M over V, that is actually equal to density. So now you can actually find the density of gases, which by the way, is really, really helpful, not because density, but because you can find the molar mass also. That's really the important part of this little manipulation of Pivner, is usually when you're in a lab and you're dealing with unknowns, you don't know the molar mass of a compound, okay? That it's an unknown, so you don't know. So you can't go like, how we find the molar mass of something, you go to the periodic table because you know what you're looking for. HCl, you go to H and you add Cl and there's your molar mass. But if it's an unknown, you don't know that. You can't do that. You can't go to the periodic table. So usually what they do is they do gas stoichiometry type experiments. So they'll find the mass of something that is easy to find, and you'll be able to find the volume it occupies, right? Because you can also measure that. If you find that, which is a physical quantity you can find in lab, you can solve using the density to find the squirrely m, which is the molar mass. So it is very, 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 very useful to be able to do this manipulation of the Pivner equation. But this is how you would find density. So if I asked you for density, this is how you would manipulate Pivner to get density. I can also ask you for the molar mass. So if I ask you for that, all you got to do is manipulate Pivner to isolate the squirrely m, the fancy m. Does everyone understand how to do that?
Yeah.
You were cutting off. Did you say yes? I can't.
Yes.
Okay, thank you. Okay, so what I want to do is I want to do some problems, yes? And I know that we've done it already, but I'm going to erase it and you're going to help me do it again, because your brain is a freaking muscle. And the more you practice doing it, the easier it becomes. So it's in the chapter. It's example 5.8. Again, the reason I'm doing these examples in the chapter is because I feel like not a lot of you guys don't do the examples in the chapter, which give you step-by-step directions on how to do it. And most of these questions are similar to the questions that I give you. So just to make it clear, I'm doing these problems. All right, so anyway, example 5.8, and it is actually on page 191. I'm doing the practice exercise. So it's really simple. It says, what is the density in grams per liter of uranium hexafluoride? What is uranium hexafluoride? Can somebody give me what that formula is?
UF6.
That's exactly right. Hexa means 6. So it's UF6, hexafluoride. So they want to know the density. They want to know the density of this at 779 millimeters of mercury and 62 degrees Celsius. Okay, so somebody volunteer and tell me first, what do I need to do? Oh my gosh. Okay, so Drew, how about you?
I'm not too sure.
It's okay. So we gotta get to density, right? And
Yeah.
all we have to start with is this. We have Pivnert to start with, but do you see anything there that says density? No, right?
No.
No. So we just did a little like conversion thing just a few seconds ago. So what can I change in this Pivnert the way it is to get what I need? What does this symbol actually stand for?
It's grams over moles, right?
Not grams over moles. That would be
Moles over
molar
grams.
mass. No, no, no,
Oh,
no, no,
I
no.
don't
N,
remember.
N stands for mass over molar mass. Grams over moles. So
Yeah.
mass over molar mass. Okay, so you would convert that first to that, and then all you're doing is substituting, right? So you would do this. All you did is substitute that N symbol for what it really is. You need to find density. What is density? What are the units of density?
Mass over volume.
Okay, so here's mass right there, and here's volume right here. So you need to get all of that together, right? Mass over volume, you need to get that. So how do you do that? Tell me how to do that.
You want the mass and volume to be on the same side and everything else on the other side?
I don't know. Are you asking me or are you telling me?
I think that's how you do it.
What is density? I mean, don't
Mass
think.
over volume.
You're exactly. So I'm trying to make a point that you know what you're supposed to do. Don't be afraid. Don't second guess yourself. Density is mass over volume. You just said it. So if I need to find density, what do I need to do?
Move over molar mass. So multiply by molar mass to move it over to the other side.
Okay, I will do that. And then what happens to that V?
You divide by that, I think. So it's M over V. And you move the
Okay,
RT also over.
multiply by it?
Divide.
Okay, there you go. See, you know exactly what to do. So now this is density. That is it. You've got it on the right side. So what does this stand for? What does that P stand for?
The pressure.
Correct. Did they give you pressure?
Is that the 779?
Oh, you better not be asking me.
Yes, it did.
Exactly, it is. Yes. That is the pressure. So you have that. What is R?
R is a constant.
Right. So you just have to know that constant. What is T?
Temperature.
Did they give you the temperature?
62 degrees Celsius.
Exactly. What is this fancy looking M?
That's the molar mass, right?
Exactly. Do you have the molar mass?
You can find it
Okay. Why? Why can you find it?
because you already have the compound.
Exactly. So all from here, all very good, Andrew. Thank you. All you do from here is just plug and chug. You have all of the information. So you've got to convert this to ATM. I don't know what that is. You got to convert this to Kelvin. I don't know what that is either. But you have all of this and you would get your M over V. So let's do it for, who was it? For Kennedy's sake, because she likes me to plug stuff in. So what is the pressure in ATM? Can somebody do that for me, please?
1.025 ATM.
Okay. And then what's the molar mass?
352 grams per mole.
Okay. What's the R is 0.082057 liter ATM mole K times temperature. What's that in Kelvin? Hello.
335.15 Kelvin.
Thank you. Is freaking she the only one that's doing these problems? Come on, guys. This is super easy. Engage. If you engage, you might learn a little bit better. So Kelvin, okay, so we need to get density. The units of density should be, oh my Lord. The units of what the frick? How do I get back? Okay, the units of density should be grams over, oh, now I'm in red. How did that happen? Should be mass over volume, which is grams over liters. That's what we should have left as units. So if you cancel everything, Kelvin, ATM cancels with this ATM, this moles cancel with this moles, and that's it. What do you have left? Grams over liters, which is density. That's it. Super easy. All right, so do you guys have any questions? You will be responsible for knowing how to well, actually, that's not even true. I believe your equation sheet has this version right here. It has that version of the Privnert equation. So really, you don't even have to learn how to manipulate it. You have to know what that is and use it correctly. So there's that. But you should feel comfortable manipulating the Privnert equation, so you can do that. In case you don't, for whatever reason, I don't know, you don't have the equation sheet. Okay, do you have any questions on this problem?
So we could leave the density in grams per liter.
Oh, that's what you do it for gases. It's grams per liter, not grams per mil, because they're so small and they occupy such a big space. The numbers are easier when you leave them in grams per liter. So what the freak, man? I don't understand. Hold on. I'm trying to delete everything quickly so I don't have to use my little pen. So I guess that's the fast way. All right, I can do that. Okay, so everybody cool with that one, or do you have any other questions besides Justin's question? You're good? Everybody, hello?
I'm good.
Okay, so the next question is basically just the next example. It's example 5.9, and again, in the chapter, and I'm doing the practice exercise. That's on page is on page 192 of your book. Okay, so sort of the same, a little different. So it says the density of a gaseous compound. So they're giving you the density. The density of a gaseous compound is 3.38 grams per liter at 40 degrees Celsius. And, oh, not done, and 1.97 ATM. So they want to know what its molar mass is. So now you have to manipulate it to get a different variable. Can someone help me do this? Please.
I'm gonna volunteer.
Thank you so much, Camille. I love volunteers. Go ahead.
So first we have to manipulate the Privnert equation.
Okay, so let's start with Privnert.
PV equals nRT, and then N is the mass over the molar mass. So you would multiply the entire thing by.
So what is this asking for? What was the question asking for? Don't get lost in the sauce. What is the question asking for?
Molar mass.
Right, so it's asking for squirrely m. That's what it's asking for. So once you substitute the little m over this fancy m, what's left? What do you have to do?
Oh, okay. So it would be PVM over RT equals 1 over swirly
Okay,
M.
you're cutting out, but what are you trying to do? Just tell me what you're trying to do. You're trying to do what?
I'm trying to isolate the swirly M.
Okay, so all you got to do, like I think that's what you were saying, but you were cutting off, is just bring this over here. That's it. And then bring these two guys over here. That's all you got to do. So in one step, you can do it like this. MRT over PV. Yes?
Yeah.
Okay, good. So once you're here, you're pretty much done. It's just that they gave you, one of the things they gave you was density, right? They gave it to you as density. So if it makes it easier for you, you might want to rearrange that to look like this. M over V times RT over P. It's the same thing. It's just since they give you this as a unit, you might want to do that so that it doesn't confuse you. But it's still the same thing. Everyone's being multiplied together and then divided, so it's not a big deal. So after here, you just plug everything they give you. So
Right.
they gave you 3.38 grams per liter. You know R, that's 0.082057 liter ATM. What is the units that I should have left at the end of this problem?
Grams per mole.
Grams
Yeah.
per mole, molar mass, exactly. What's 273 plus 40? Is that 303, 313, 313, I think, Kelvin. Then divided by P, which is
It's 13.
yeah, 313, 1.97 ATM. And then that's it. You basically just cancel everything, ATM, ATM, K, K, liter, liter. What's left? Grams per mole. So there you go. You have your answer in grams per mole. Okay? It's simple. I hope you guys think this is simple because this all this is just a plug and chug of a different version of Pivmer. Do you guys have, but even though if you don't think it's simple, do you guys have any questions on this?
Will pressure ever be given in pounds per square inch?
Maybe.
Okay.
I think I did that once in an exam, but all it is just a conversion. You got to convert it. I would give you the stuff to convert it. You just need to convert it. But okay, so now what I want to do is I want to do one more, right? So this one's a little bit more complicated. Has a lot of stuff. And it's a blast from, oh, no. Let me see if I can just do what I did before. Oh, there you go. Okay, I haven't, okay, there you go. So it's the next example on page 193. So example 5.10, but it's the practice exercise. So at the end of the little box, it says a gaseous compound. So this one's a little long, so you got to stay with me, okay? It says a gaseous compound is 78.14% boron, 21.86% hydrogen. What is already, you should have some feeling like a percent. What does that remind you of?
Percent composition.
Okay, but what else? Everyone always says that. That's the easy thing. What else should it remind you of? What's another thing you use? Sorry, say it again.
Empirical formula.
Exactly, an empirical formula. And percent composition is the easy version, Camille. What it should remind you is the hard thing, which is the empirical formula. That's exactly what this problem is going to deal with, empirical formula. So a gaseous compound is 78.14% boron, 21.86% hydrogen. At 27 degrees Celsius, 74.3 milliliters of the gas exerted a pressure of 1.12 atm. If the mass of the gas is 0.0934 grams, what is the molecular formula? So that's a lot of information. But this is a very easy problem, and you are expected to do these easy problems. It's the same type of problem as an empirical formula in chapter 4. It is. It just now has a little bit extra of information. So you have 78.14% boron. You got 21.86% hydrogen. And then this is the other information. You got 27 degrees Celsius, you got 74.3 milliliters, 1.12 ATM. So they give you a bunch of stuff. They give you volume, temperature, pressure, and then they also give you, if the mass of the gas is 0.0934 grams, what's the molecular formula? So they want to find the molecular formula of this thing. You got to help me do this. What is the first thing you should do?
Change the percents into grams.
Okay. After you do that, I'm just going to go ahead and erase and put grams. Great. Now what do we do?
Then you find the molar mass, or change them to moles. Change the grams to moles.
Thank you. So you would change it to moles. So you would use the molar mass for that. What's the molar mass of boron is 10.81, I believe. Grams of boron is 1 mole of boron. This guy is 1.008 grams of hydrogen is 1 mole of hydrogen. So I need people to do this for me, please. What's the moles of boron?
For boron, I got 7.228. Well, 7.23.
228 is better. Remember, empirical formulas, you don't cut them off. 7.228 moles of boron. Okay, what's for hydrogen? Should be like 20.
1.6865.
You said 1? No, impossible.
21.
Ah, okay. 21 point, what'd you say?
6865.
6865. Okay, moles of hydrogen. Now, class, children, my beautiful scientists, what do we do?
Divided by boron.
Divided by boron, because it's the smallest, right? So if I do that, I divide everybody by boron. So that means I would get 1 for boron. And then what would I get for hydrogen? Should be
3.
Right, 3, right. So what is this? What is this that we have just found?
The formula.
No, what formula?
The empirical formula.
Thank you. Okay, so the empirical formula, right. So if we were in chapter 4 and I asked you to find the molecular formula, forgetting this whole Pivner information on the left here. If we were here in chapter 4, what information would you need to get to the molecular formula?
Mass of the molecular formula.
Exactly. You would need mass of the molecular formula. So right here, you have the empirical formula. Why the hell do you think they gave you all of this information?
To find the mass of the molecular formula.
Correct. So if they give you all, see, you have to remember, we always will use the things from previous chapters. So you can't forget them. We will always see these things coming up again. Nomenclature always, redox, limiting reagents, all these things will come up again and again and again. So it's just a little different. So yes, at this point, you would need molar mass. How do you find molar mass? You look at all this information they give you about the Pivner equation. What did you just learn? One of the manipulations of the Pivner equation gives you what? Kangadi, say it.
No, what did you say? Say it one more time.
So one of the it's a hard thing to say. One of the manipulations of Pivnert gives you what?
The
What did we just do?
I know it's the squiggly M, but I can't remember what it's.
What is that? What is squiggly M?
Molar mass.
Thank you. Thank you. Okay, so we have to, for empirical formula, at this point, you would need the molar mass to get the molecular formula. The squiggly M, you guys have to remember these freaking symbols, bro. It's not that hard. I'm not telling you to learn freaking calculus. Squiggly M is molar mass. So you would solve Pivner for molar mass, okay? So I'm not gonna ask you step by step because I hope that you guys already we've seen it already a couple times. So RT, PV, you need to solve for this because you need the molar mass. And if you do that, you would get molar mass on one side and you would get MRT over PV. If you notice, you have everything else. You have mass, you know R, they gave you T, you know P, and you know V. So now this question becomes super simple, but you have to be able to understand what all this information that they give you is for. So if I plug all that in, I should get 0.0934 grams. R is 0.082057 liter ATM, mol K. T is, what is that, 300.15 Kelvin, over P, which is, where's my P? Oh, 1.12 ATM. And then volume, which is not milliliters, but liters. So 0.0743 liters. Cancel all this out. Liters, where's my liters? Liters, ATM, ATM, KK, I'm left with grams over moles. What is the answer? What is my molar mass? Hello.
$27.04 grams per mole.
Thank you, Cherish. 27 point, say that again.
0.04 grams per mole.
Okay. Now, what do I do? Because we're not done. At this point, if you were in chapter 4, I would have given you this information. And then what do you do to get the molecular formula?
Divide or multiply depending on where you started.
Divide what? What are you talking about? Be more specific.
Oh, you would divide the empirical formula into the molecular formula to get the integer coefficients and then multiply that by the empirical formula.
So first, before we divide, what do we have to get? What do we have to find out?
The mass of the empirical formula.
Yes. So what is the mass of the empirical formula? 13, maybe, some 13 point something.
$13.834 grams per mole.
Thank you. Okay, now that is what the mass is of the empirical dude, like Justin said. Then we would take the mass of the molar of a real thing and divide it by the mass of the empirical to see how many times the empirical fits into the molecular. If you do that, if you take 27 and divide it by 13, you should get 2. So that means that everything here in the empirical gets multiplied times 2. Times 2. So your molecular formula would be B2H6. So you guys, I don't know, maybe you're tired just like me, you're sleepy, but you guys have to talk to me because does anybody not understand this? Does anybody need help with any particular part? Because if not, I'm going to move on.
I'm sorry, I did miss the last part. Why is it multiplied by 2?
We used the Pivner information to get molar mass of the actual compound. So this is what the actual molecular formula weighs, right? So what we found, we had to take what the actual formula weighs. We gotta and we gotta find what the empirical formula weighs. We gotta see how many times the empirical formula fits into the actual formula, the 27. So you would divide it. You would take 27 divided by 13. That's 2. So that means that the empirical formula needs to be multiplied times 2 to get to the actual molecular formula. Because if you take the molar mass of B2H6, it'll equal 27.
Okay.
Does that make sense?
Mm-hmm.
Are you sure?
Yes.
Okay. Any other questions?
I have a question.
Yes.
How did we get R? The
R is
constant.
given. R is given. You don't get R. R is always the same. This 0.082057 is always the same. It's on your sheet.
Okay.
Yeah, so you don't worry about R. R is a constant and it will always be that number with those units, at least for this class.
Okay. Thank you.
You're welcome. Any other questions? No. Okay, so I want to do another one. And I feel like I'm gonna get frustrated with this one, but hopefully you guys will engage. Oh no, this is why it was clear, is because discard. Can I do that? Yes. Okay. Perfect. So I want to do one more. Right, and this is the one that I was talking about that applies one of the laws. So it is the next example. It's example 5.11, but it's on the practice exercise is on page 194. So it's very short, but let me read it. It says, assuming, and it's important that you listen, right? So assuming no change in temperature and pressure, calculate the volume of oxygen gas required for the complete combustion of 14.9 liters of butane. And then they give you a reaction. So let me write the reaction and then I'll read it again. So it's 2C4H10, right? Plus 1302. This is gas, goes to, so this is a combustion. It goes to, what does it say? 8 CO2 gas plus water. How many waters? 10 water. Liquid. Okay, so let me read it one more time. Assuming there's no change in temperature or pressure, calculate the volume of O2, so they want to know this, volume of O2, for the complete combustion of 14.9 liters of butane. So all they give you is that information. Can anybody tell me where to start, how to do this? And by the way, as a preface, this is a one-step problem. Okay, so it's not hard. You just have to learn to understand what they're asking and try to apply the stuff that you've learned. Specifically, I'm going to give you a clue, the laws. There's one law here that you can use to your advantage to get the one-step thing that you have to do. So how do I start? How do I start every problem in chapter 5?
Pivner?
Good choice. Pivner. So let's write Pivner. Let's start with that. And is there anything that I can do from here?
They told you that pressure. Well, they told you to assume that pressure and temperature are constant. Although I'm not sure that it would be in real life, but
Assuming, right? It's not, because this is a combustion, so it won't be. But assuming, assuming that the change in temperature and pressure do not change. Actually, you can do it in a what do you call that? In a bomb, in a calorimeter bomb. Then you can control the pressure. But that's neither here nor there. So anyway, assuming pressure and temperature is constant. So what does that mean, scientists? What can I do? How does that help me in my equation, in my problem seeking?
You can take it out.
Yes. So pressure and temperature is constant. So therefore, I don't have to worry about it. What else? How about Kennedy? What else do you think I can do?
What else can you cross out?
Yeah.
Can't you cross out R?
Why?
Because it's always constant.
Correct. So what are you left with? You're left with V and N. Does anybody remember? Does this remind you of anything?
Avogadro's law.
Avogadro's law. What does Avogadro's law tell you?
that 1 mole, that 1 mole of any, well, it's something like, never mind. It has to do with volume and gases and the moles and them being equal.
Right, and it doesn't take a super smart person, but look at what does it tell you? Look at the equation that we're left with. What does it tell you? Just in simple terms.
Volume equals moles.
Yes. So when you have constant at the same temperature and pressure, the number of moles of a gas is going to be directly proportional, directly related to its volume, regardless of what that gas is. It doesn't matter that they're different gases, which is why Avogadro is so freaking phenom. So knowing that information, because you guys don't just have to memorize things, you have to think, right? Like think. So if you know that, and all they give you in this problem, they want to know the volume of O2 that you need to combust, right, to do this. But all they give you is this. I mean, you literally only have this. So how can you use that information in Avogadro's law to help you find it? To help you find the answer or the volume of O2 needed to combust that many liters of butane.
I'm gonna go out on a limb here and say that you start with 14.9 and you go to O2 and you use the mole to mole ratio somewhere in there.
That is not on a limb. That is exactly what you do, except this is what's kind of tricky for students, is that volume is directly related to moles, right? So what they give you, they don't get, oh Lord, they don't give you moles, right? They get, the starting material is liters, right? They don't give you moles, but they're directly related. So that means at 14.9 liters, if you look at the balanced equation, you can say that there's 2 moles of butane, right? But if there's 2 moles of butane, according to Avogadro's law, how many liters of butane are there?
14.9.
No. Okay, so look, 14.9 is the starting material. Starting, so right? That's a butane. That's a butane. But that's the starting material. That's how much. But remember, this is the balanced equation. So my question, and stick just to my question. My question is, if I have 2 moles of butane in this balanced equation, how many liters of butane would I have in this balanced equation?
2.
Oh.
Yes, 2. Look, this is it right here. It's equal. Yes, so that's the answer. The answer is, if there's 2 moles of butane, that means that you're using 2 liters of butane in this balanced equation. Do you understand that? Because that's what the law says, assuming that temperature and pressure are constant. So you can literally write okay, if I'm with butane and I need to figure out how much liters of oxygen I would do, okay, look at the balanced equation. I have 2 liters of C4H10, right? Because liters is the same thing as moles when everything else is constant. And it's like I'm doing a mole to mole ratio, like what Camille said, but it's not mole to mole, it's liter to liter, right? So if I have 2 moles of, for every 2 moles or every 2 liters of butane, I need how many liters of O2 to combine with that?
That makes
You got cut off. Stop, leave your microphone on. What did you say?
that makes sense.
Are you sure? So all we're doing is applying, I mean, literally it's a one step. All you're doing is multiplying 14.9 times 13 divided by 2. Why can you do that? You can't do that always, okay? You can only do that when you're applying Avogadro's law. When you have pressure and temperature being constant, you can use this. Because there's nothing else you can do. How else are you gonna find the volume if all they give you is the volume? You don't have nothing else. You don't have pressure, you don't have temperature, they don't give you they don't give you anything. So you have to apply this law to get to the answer. All you're doing is you're doing like a quote unquote mole to mole ratio, but really you're just using the unit of liters because you can use his law, V is equal to N. So I hope this is not so super confusing. I hope you understand that, because you are going to need to be able to apply these laws, right? So you got to know when they give you something, the first thing you should do is, yes, write Pivner. The second thing you should do is, can I cancel anything? Don't just, because Cherish, that was your first thing when you told me in the first problem, well, let's cancel, but don't necessarily cancel. Can you cancel, right? Or is that really the first step that you should do? Well, here there's no choice. And they tell you assume this and this. So I would definitely always cancel if they tell you to assume it. So that's it. That would be the answer you would just multiply, divide. That would be the answer to that question. Do you have any questions? Any concerns?
It's more of a conceptual question, but why does it take so much oxygen to combust? What's the name of the molecule? Butane?
I've never combusted butane, so it's a stoichiometric thing. It probably has to do with, butane is a lot, it's pretty large compared to O2. So maybe you need a lot more of oxygen gas to fuel it. So, it's a large alkane. So it might not seem large, but it is a large alkane when you have, only 16 per oxygen or whatever, 32 per oxygen. So I just think it's because it's a big compound. I think if you have even bigger alkanes, you'll have a bigger proportion of oxygen gas to fuel it. That's my guess.
Yeah, because I remember it being 25 moles of oxygen gas for octane.
Yeah, there you go. Exactly. Almost half, right? So almost twice, my bad. So any other questions? Okay, so it's almost time to go, but I have 1 minute. So I'm not gonna do it. I'm just gonna show you. Tomorrow we're gonna do, and I didn't get as far as I wanted to, but we're gonna start the conversation of partial pressure, and we're gonna finish the conversation of partial pressure. Partial pressure is not hard, but I know you guys are gonna hate it. You're gonna freaking hate it, because if I just show you, look at this slide. We're gonna go over the slide, and you guys are gonna hate it. Because look at all these freaking variables. I know you're gonna hate it, but I just want to preface it by telling you it's not hard. It is not hard. The concept is not hard. What is the concept of partial pressure? Right here, literally. So if all it says is that if you have a container and you have a mixture of gases in there, right? Like it's not just one gas, you've got oxygen, you got nitrogen, you got something else, whatever. You have a mixture of gases in one container. And I wanted to find the total pressure of everybody, of that container. I got to add everybody's pressure, individual pressures up to get the total pressure. That's all this is saying, right? So the total pressure of a container is equal to how many different things are in there, the pressures of how many things are in there. If you understand that concept, then partial pressure is not hard. It's just you've got to learn, little what is it called? I can't remember the word, but eccentricities or whatever, little logistics of how to do that. But the general fundamental concept is partial pressure is if you want to find the total pressure of something, you take up everybody's partial pressure and you add them up. But at the same time, you can also find the partial pressure. If you know the total pressure of the container, you can find the individual pressures of everybody by also using a derivative of this equation. All right, so that's what we're going to learn tomorrow. And I beg you to look it over tonight so that tomorrow you're not completely lost and are seeing it for the first time, because you're going to need time to practice partial pressure. I'm telling you. So start reading it now, and I try to do some problems before we get to class tomorrow, so you're not completely lost and you're not like trying to catch up. All right. So I'm going to stop sharing. Do you guys have any questions? So we are effectively like actively losing people. Now there's only 11 of you, and I think that there's been 11 of you for the last week. So I don't know what's going on. But anyway, if you guys have no other questions, then I will let you go because it's 4:32.
Is there a study session tonight or no?
Yeah, there is. I'll be there.
Okay.
Can I schedule a separate one? Because I can't make it tonight because of a family emergency.
So you can schedule an office hour.
Okay.
Your microphone's really like loud. I don't know. It's like really bad. You might maybe, do you have headphones on or no?
No.
You might try to put headphones. Maybe that'll be better with the microphone. I don't know.
Okay.
It sounds like hard. Thank you. So yeah, just email me and we can get together. Have
a nice day.
Thank you, Cherish. You too. Anybody else?
Thank you. Have a good day.
All right, guys. All right. See ya.